So a simple review of Oxiranes or epoxides. And this kind of slide basically says it all, right? If you have basic conditions, you have a strong nucleophile. In that case, steric effects are the most important, right? It's all about steric effects, and you get that trans product, right? It doesn't matter what the nucleophile is. It could be a Grignard, it could be H-, anything with a negative charge. A stronger nucleophile is going to react in SN2, so you get that trans backside attack product. If you're in acidic conditions, it's different. Now, in acidic conditions, you don't have a good nucleophile. Your epoxide is actually your nucleophile in the first step, and the first step is protonation, right? In that case, the most substituted carbon is most reactive because it's the most delta plus, able to stabilize that delta plus charge. No carbocations, but then the nucleophile can come in, not a very reactive nucleophile, something like water, an alcohol, maybe I-, Br-, can come in, do the SN2 there, and again, you still get the trans relationship, but on the opposite carbon. This is called regioselectivity. Why is it called regioselective? You're picking one region of the epoxide over the other. You're selecting one. By picking the conditions, you can get one region of the epoxide to react versus the other. Some might ask, why are epoxides reactive? Ethers aren't that reactive. You're right, ethers are not that reactive. We use diethyl ether as a solvent a lot of times in lab. What's so special about an epoxide? Well, it's really about the bond angles. Right? A three-membered ring, right, is not very happy. This is an sp3 hybridized atom. The bond angle for a tetrahedral sp3 hybridized atom is 109.5. Equilateral triangle, that's a 60 degrees right there. That's unhappy. It's not able to share its electrons like it wants to. It has to be kind of at an angle. That makes that much more reactive than a regular ether. Right? That's the key there. That epoxides are higher in energy, so they're more reactive to that. And that doesn't matter acidic or basic conditions. Epoxides are reactive because of ring strain. Here's just simply a bunch of examples. Again, these are all the same, but it's an exercise in numbering your carbons. What people will goof up, invariably what people will goof up is they'll have the nucleophile attack and they'll break the wrong bond of the epoxide. That's what people will do. They'll have this come here and they'll break this bond, right? Number your atoms. Be very careful, right? Again, this is just going blow by blow. You protonate the epoxide in acidic conditions. That makes it even more reactive, even better leaving group, because now you're in acidic conditions. So it always goes for the most substituted. They talk about you could do it with just alcohol, H+ and water, H+ with an alcohol. So in water and H+, you get a diol, two alcohols. With H+ and an alcohol, you get an alcohol and an ether. And the one we've seen a lot already, if you used HCl, HBr, HI, you get the alcohol, a halohydrin is called, alcohol and the halogen. Always trans to each other. Always trans. Always trans. Believe it or not, you've seen this before multiple times, as a matter of fact, in different situations. You saw it with mercurium ions, where it went for the more substituted carbon. You saw it with bromonium ions, where it went for the more substituted carbon. And now you're seeing it in epoxides, right? Plus charge on the thing and the ring goes to the more substituted one. And so you've seen this before. And again, in all these cases, also that trans SN2 type geometry following the reaction. So now here's just showing you that it is regioselective, and this is why it matters. Let's say you have a regio center, a chiral center. Let's say you have a chiral center. What's going to happen is when you protonate in acidic conditions, if that's the position you're going to react with, you're going to end up with, right, inversion of stereochemistry, right? Because, right, you're going to do an SN2 reaction. If this was R, right, if this was R, when you do an SN2, what's going to happen to the site? It's going to be inverted. Do I need to do the thing? Oh, that hurts. That really, oh man. Yeah, it's like my femur just cracked. Ouch, buddy. Yeah. Right, inversion. You're going to do an SN2, so stereochemistry matters when you do have a chiral center. This is a little more complicated, maybe beyond the scope of what we're thinking about. But what can happen is if you had epoxides, right, in theory, you could have the left-handed epoxide and the right-handed epoxide, right? You could have both enantiomers. And then if you did an SN2, what are you going to get, right? You're going to get a set of enantiomers again. So they call this stereospecific, that the SR is going to turn into the SS, that stereoisomer is going to react in a specific way, right? Stereospecific. The R version reacts differently than the S version. That's all this is saying, right? So just lay that out there too. Here it is. Again, here's the slide that tells it all. Basic conditions, less substituted carbon. It's all about sterics. SN2, trans, protonation. Acidic conditions. Protonation, react with the more substituted carbon, give the trans following the SN2 as well. Different regioselectivity for this.